Tactile sensing is one of the modalities humans rely on heavily to perceive the world. Working with vision, this modality refines local geometry, measures deformation at the contact area, and indicates hand-object contact state. Leveraging tactile sensors such as digit, we propose a novel visual-tactile and hand-object reconstruction framework VTacO and extend it to VTacOH for hand-object reconstruction. We also propose a simulation environment, VTSim, which supports generating hand-object interaction for both rigid and deformable objects. Extensive experiments demonstrate that our method outperforms the previous baselines qualitatively and quantitatively. Finally, we apply our model trained in simulation to real-world cases which display qualitative results. We consider the problem of 3D reconstruction of in-hand objects from a visual-tactile perspective, with which we propose VTacO, a novel deep learning-based visual-tactile learning framework. In this setting, we assume the visual input is a 3D point cloud of an in-hand object converted from a depth image. The tactile input contains n tuples of tactile readings obtained from the sensors, which contain RGB tactile images and 6 DOF sensor poses. The object shape is modeled by the winding number field, a variant of the signed distance field. Thus, we can also learn the object representation similar to the SDF-based pipelines. The point cloud is converted to a global feature through a feature extractor FP. The tactile image is forwarded to another feature extractor FT to obtain local feature. Then we sample M positions in the 3D space and fuse the global feature to each position, local feature to the near positions according to the sensor poses. The final feature will be passed to a pointwise decoder to predict the winding number value, which will be used for extracting the shape by Marching-Cube's algorithm. Considering the digit sensor does not provide the sensor pose, we provide two different options to obtain sensor poses in the real world by attaching markers or inferring from hand kinematics. In order to estimating sensor poses by markers, we follow the practice in pose estimation and print Aruco tags and attach them to fingertips. Then we estimate the fingertip poses by estimating the pose of tags. We adopt OpenCV to implement the pose estimation. For the latter option, since the input point cloud contains a view of the in-hand object, it allows us to reconstruct the hand alongside the object. We can infer the poses of tactile sensors based on the prior that they are attached to the fingertips. We can infer the poses with hand kinematics. To jointly learn visual-tactile hand-object reconstruction, we introduce VTacOH. We model the hand by the monomodel with hand shape and hand joints parameters. In the process of tactile position sampling for every inferred digit position, we simply query the sphere centered in the local point clouds generated from the tactile sensors with a radius r equals 0, 1. The feature fusion remains the same. We adopt a sim-to-real transfer paradigm to learn the visual-tactile learning task, since obtaining information about object deformation in the real world is hard. And recently, many simulation environments have proved to be effective on soft body object simulation with Unity. We present VTSim, a simulation environment based on Unity to produce training samples of hand-object interaction with ground truths of WNF, visual depth images, tactile signals, and sensor poses effectively. The dataset synthesis process is divided into 3 parts: hand pose acquisition, interaction simulation, and recording setup. We first use GraspIt to obtain various hand poses and replay the configurations in Unity with collision and model the rigid object with rigid body, the soft object with OBI in XPPD-based physics engine. We transplant the implementation of the digit camera from TACTO to obtain tactile images and set RGBD cameras on 8 different viewpoints to generate input point cloud. The winding number fields are generated by library IGL. The benchmarks we use are YCB objects models and KB48 objects models, which both provide full model meshes and texture for our reconstruction task. We conduct plenty of experiments to show the capability of VTacO. We compare our results with the Visual-Tactile baseline 3D shape reconstruction from vision and touch. Since this work didn't study the reconstruction of deformable objects, we only compare the 3 non-deformable categories: folding racks, locks, and scissors. We also report the object reconstruction result for VTacOH setting. Due to the accurate hand pose estimation, the results of VTacOH are only slightly worse than the VTacO, where the sensor poses are the ground truth. We can see from the table that our method outperforms others in most categories in the metrics. Qualitative results are demonstrated in the figure above. As illustrated in both quantitative and qualitative results, VTacO has better reconstruction results. Plenty of Latian study on May aspects such as the comparison with pure vision method, procedural tactile embedding, visual feature encoder choices, and fusion strategies demonstrate the effectiveness of our model. We validate the performance of learned VTacO in the real-world data. We select 3 unseen boxes, 3 unseen bottles, and 3 unseen locks to demonstrate the deformable object reconstruction. To note, the selected objects are not used in training from simulation. We adopt an Intel RealSense L515 camera mounted on a fixed tripod to capture the depth observation. In the real world, we attach 2-digit sensors to the hand and detect the sensor poses according to markers attached to the tips. Since we observe noise and shadows in real sensor readings, we augment the tactile images in simulation to match real RGB distribution by adding noise and adjusting contrast. We filter out the point cloud around the in-hand object manually and use it as input. We can see in the figure that objects from 3 categories have been well reconstructed. In conclusion, we propose a novel Visual-Tactile in-hand object reconstruction framework, VTacO, and its extended version, VTacOH. Our proposed frameworks can reconstruct both rigid and non-rigid objects. The Visual-Tactile fusion strategy allows the framework to outperform the baseline methods and reconstruct the object geometry details incrementally. In the future, we are interested to leverage such features in robotics experiments to better estimate the object geometry in manipulation,